It's 1946. America is celebrating victory, factories are roaring back to life, and Detroit's legendary Ford Flathead V8 is still the king of the streets, powering everything from moonshine runners to war heroes' daily drivers. But deep inside those iconic engines, a hidden flaw is quietly destroying them, melting exhaust valves, cracking heads, turning reliable powerhouses into expensive scrap metal. Ford's own engineers know about it. They've written the memos, seen the failures, but they're too proud, too invested to admit the truth. Then, in a tiny machine shop on Chicago's South Side, a quiet Russian immigrant with nothing but a lathe, a slide rule, and some old Soviet engineering training, discovers a fix so brilliantly simple that it will save the Flathead, dominate the dry lakes, and make the entire American automotive industry look foolish. This is the true story of how one man outsmarted Detroit's best designers. With a hack so elegant, Ford would spend years trying to figure out how he did it, and then quietly steal the idea. I'm Jack, and today on Torque Saga, you're going to learn the brilliant Ford Flathead hack that changed hot rodding forever. By 1946, Ford's Flathead V8 was a legend. For over 14 years, it had been the heartbeat of American performance. The first affordable V8, the engine that made hot rodding possible. Bootleggers loved it for its torque. The military loved it for its reliability during the war. Returning GIs were snapping up cheap 32 to 40 Fords and turning them into street machines. On the surface, everything looked perfect. But underneath those polished valve covers, the Flathead was dying, and dying fast. The problem wasn't lack of power or poor build quality. It was physics. Pure, unforgiving thermodynamics. The Flathead's combustion chambers were shaped like upside-down bathtubs cast right into the block. The spark plug sat off to the side, forcing the flame front to travel sideways, swirling around deep valve pockets, fighting turbulence and heat soak the entire way. At low RPMs, it was fine, smooth, tractable, almost gentlemanly. But the moment you pushed past 4,000 revolutions per minute, the engine turned into a heat pump from hell. Exhaust valves would glow cherry red, literally glowing, visible through the spark plug holes if you were brave enough to look. Cylinder heads cracked like glass. Valve seats pounded themselves loose. Detonation was so violent it could turn pistons into abstract art. Hot rodders were replacing exhaust valves every few thousand miles because the intense heat eroded them away like sugar in rain. Stock Flatheads ran exhaust valve temperatures well over 1,500 degrees Fahrenheit. At those temps, even good cast iron starts to lose strength. The metal softens, valves warp, seats recess, and eventually the whole engine grenades itself. Detroit knew. Internal Ford memos from 1945 to 46 are full of failure reports, charts, graphs, dyno logs, all documenting catastrophic heat-related issues. Engineers wrote about cracked heads piling up in warranty claims. They knew the architecture was the culprit. But here's the thing, Ford didn't care. The Flathead was cheap to produce. Tooling was paid for decades ago. Millions of wartime mechanics knew how to fix them. And most importantly, admitting the design was flawed would mean admitting Henry Ford's genius engine had a fatal defect. Ford simply didn't do that, ever. So they kept building them exactly the same way while hot rodders paid the price. The aftermarket tried everything. Massive radiators that looked like barn doors. Exotic racing fuels that cost more per gallon than whiskey. Custom copper head gaskets, asbestos gaskets, even experimental aluminum ones sealed with prayers and high hopes. Nothing worked. You couldn't bolt on your way out of bad architecture. By mid-1946, the smart money was betting the Flathead was finished. Overhead valve V8s were coming. Cadillac had one in the works, Oldsmobile too, and Chrysler was developing their legendary Hemi. The writing was on the wall. The Flathead's days were numbered, until a quiet Russian machinist in a Chicago back-alley shop looked at the problem differently than anyone in Detroit ever had. Viktor Konstantinov was nobody's idea of an automotive revolutionary. Born in Moscow in 1908, he grew up in the young Soviet Union and trained at one of their top technical schools. In the 1930s, he designed agricultural machinery, big, slow, brutally utilitarian tractors that had to keep running no matter what, because spare parts were scarce and downtime meant people didn't eat. Soviet engineering wasn't about glamour or record-breaking horsepower. It was about survival. You made things work with whatever you had, using clever design instead of expensive materials or endless resources. In 1943, with the war still raging, Viktor escaped the Soviet Union through a dangerous, roundabout route, Turkey, Britain, and finally America. Like many who left during those years, he never talked much about how he got out. Some stories are safer left buried. By 1946, he was living quietly in a boarding house on Chicago's South Side, working as a machinist in a small speed shop that catered to local hot rodders. The California suppliers were too far and too expensive for most Midwest guys, so they brought their cylinder heads, cranks, and cracked blocks to little shops like this one. Victor kept to himself. He spoke English with a thick Russian accent that made some customers assume he didn't know much, a mistake they only made once. The other machinists just called him the Russian and left him alone. He worked with almost obsessive precision, measuring twice, cutting once, running his lathe like it was an extension of his hands. Nights and weekends? More work. No family, no social life, just the shop, the boarding house, and the constant hum of machinery. But Victor had one massive advantage over every engineer in Detroit and every hot rodder in America. He'd been trained to solve problems without money, without fancy alloys, without the luxury of throwing bigger parts at the issue. In the Soviet system, efficiency wasn't optional. It was the only option. Spring of 1946. A regular customer, a young guy trying to build a serious lakes racer, walked in dragging a pair of badly cracked flathead heads. It was the 8th failed set that season. He'd melted valves, detonated pistons, and blown head gaskets faster than he could pay for new ones. He was done. Ready to give up, sell the project, maybe switch to a Buick Straight 8 or just buy a decent used Hudson and call it a day. He told Victor, "These heads are trash. The engine's a lost cause." Victor looked at the cracked castings for a long moment, turned them over in his hands, and said in his heavy accent, "Leave them here. Give me 2 weeks." The customer figured he had nothing to lose. What Victor did over those 2 weeks would save the Flathead V8 from the scrap heap, send shockwaves through the hot rodding world, and quietly humiliate the brightest minds in Dearborn. But to understand why his solution worked, you first have to see what he saw, something Detroit's entire engineering staff had looked at for over a decade and completely missed. The secret modification. Here's the part everyone wants to know. What exactly did Viktor Konstantinov do to fix the Flathead's death sentence? It was so ridiculously simple that when people first heard about it, most thought it was a joke. Some even accused him of hiding the real secret. He blocked off parts of the water jackets around the exhaust ports and redirected the coolant flow primarily to the intake side of the block. That's it. No new cylinder heads. No exotic alloys. No overhead valves. No superchargers or fuel injection. Just carefully machined brass plugs inserted into specific coolant passages, plus precise calculations to control exactly how much flow was restricted and where it was rerouted. Think about that for a second. Detroit had hundreds of engineers, million-dollar test facilities, wind tunnels, dynamometers, and decades of experience. They tried everything to tame the Flathead's heat problem. And a quiet Russian machinist in a tiny Chicago shop solved it with brass plugs and a lathe. But here's why it wasn't just random blocking, it was pure genius. Victor realized the real killer wasn't the bathtub combustion chambers. That was a symptom. The core issue was heat distribution. In the stock Flathead, exhaust ports ran right through the block, surrounded by water jackets that tried desperately to cool them. Exhaust gases come out at over 2,000 degrees Fahrenheit. No amount of coolant was ever going to cool that effectively. All it did was boil the water, heat the entire block, and worst of all, transfer that exhaust heat directly into the incoming air-fuel charge on the intake side. It was backwards. You were preheating the intake charge with exhaust heat, exactly what you never want. Victor flipped the script. He deliberately let the exhaust port area run hotter by reducing coolant flow there. That sounds insane at first. Why make the hottest part even hotter? Because exhaust gases are already scorching. Letting the surrounding metal stay hot reduced thermal shock, cut down on expansion/contraction cycles, and stop the cracking and valve seat pounding. At the same time, he redirected nearly all the cooling capacity to the intake side and the combustion chamber areas. Cooler intake ports meant colder, denser incoming air, which means more power and far less detonation risk. He wasn't fighting the engine's natural heat pattern anymore. He was working with it. His first modified 239 cubic inch Flathead, built for that frustrated lakes racer, made 160 honest horsepower at 5,000 revolutions per minute on a dyno on ordinary pump gas. A healthy stock Flathead struggled to hit 100 horsepower at 4,000 revolutions per minute before it started melting itself. And it didn't just make more power. It made that power for hours without glowing valves, without cracking heads, without any of the usual Flathead self-destruction. In August 1946, that same car hit the Bonneville Salt Flats. With nothing more than Victor's coolant modification and a stock displacement engine, It ran 138 miles per hour, shattering what anyone thought was possible with a flathead on pump gas. The hot rodding world didn't just take notice. It lost its mind. Word spread fast. Racers started showing up at that little Southside Chicago shop, cash in hand, begging for the same treatment. They called it the Russian hack. Victor called it thermal optimization, very Soviet, very dry. But whatever you called it, it worked. And once people saw the results with their own eyes, there was no going back. The Flathead wasn't dead after all. It had just been waiting for someone who understood heat better than Detroit ever had. The technical genius behind the hack. To truly appreciate what Victor pulled off, you need to understand how heat really works inside an internal combustion engine. I promise this won't be a boring lecture, because once you see it Victor's way, it's almost impossible not to call it brilliant. Every engine is fundamentally a heat pump. You burn fuel, most of the energy turns into heat, and only a small fraction becomes useful horsepower. The trick isn't making more heat, it's managing the heat you already have. Detroit's philosophy was simple: cool everything evenly. Water jackets all around the cylinders, around the exhaust ports, around the combustion chambers, uniform cooling for uniform temperatures. Sounds logical, right? Treat every part the same. Except different parts of the engine experience wildly different heat loads. Exhaust gases leave the cylinder at over 2000 degrees Fahrenheit. The metal around the exhaust ports and valves has to live in that inferno every firing cycle. Intake air, on the other hand, comes in at ambient temperature, and you want it to stay as cold as possible because cold air is dense air, and dense air makes power. Stock Flathead design did the opposite of what physics wanted. By surrounding the exhaust ports with water jackets, it tried to cool parts that couldn't effectively be cooled, while that same coolant picked up exhaust heat and carried it straight to the intake side, preheating the incoming charge. The result? Massive temperature gradients across the block. Exhaust side 200 degrees Fahrenheit hotter than intake side, causing warping, cracking, and constant thermal stress. Victor's insight was revolutionary in its simplicity: stop fighting nature. Work with it. He allowed the exhaust port area to run hotter by restricting coolant there. The metal stayed closer to exhaust gas temperature, reducing thermal shock, cutting expansion/contraction cycles that cracked heads and pounded out valve seats. Hotter exhaust ports also kept gases expanded longer, improving scavenging and flow. Meanwhile, he sent nearly all the coolant to the intake side and combustion chamber roofs. Intake ports dropped roughly 30 to 40 degrees Fahrenheit compared to stock. That's huge. Basic thermodynamics tells us, for every 10 degrees Celsius 18 degrees Fahrenheit you cool the intake charge, you gain about 3% more air density. Victor's mod cooled the intake by around 30 to 35 degrees Fahrenheit. That's nearly 10% more air molecules packed into every cylinder, translating directly into 10% more power with zero mechanical changes. But the real magic was in the deliberate thermal gradient he created. Instead of extreme hot spots and cold spots fighting each other, he engineered a smooth, predictable transition: hot exhaust side, cold intake side, with trapped air pockets from blocked passages, acting as natural insulators. Air is actually an excellent thermal barrier, better than many exotic coatings of the era. Valve seat recession, the nightmare that killed high-performance flatheads, practically vanished. But consistent temperatures meant far less thermal cycling. Valves and seats expanded and contracted together instead of beating each other to death. Every brass plug was precisely sized and placed. Too much restriction and you'd overheat the exhaust side. Too little and you'd lose the gradient benefits. Victor spent weeks on a borrowed dyno testing configurations, measuring temperatures with thermocouples, doing hand calculations with slide rule and Soviet thermodynamics textbooks. The result? An engine that made significantly more power, ran cooler overall under load, lasted dramatically longer, resisted detonation, and even used less fuel because combustion was cleaner and more efficient. All from redirecting coolant. No new castings. No rare metals. Just deeper understanding of heat transfer than anyone in Detroit had applied to the Flathead. It wasn't that Victor was smarter than Ford's engineers. He just wasn't constrained by, "That's how we've always done it." He looked at the problem fresh, with Soviet-trained eyes that saw efficiency as survival, not an option. And in doing so, he didn't just save the Flathead. He changed how the world thought about engine cooling forever. Once Victor's modifications started hitting the streets and the strips, the numbers spoke louder than any argument ever could. A bone-stock 239 cubic inch Flathead in 1946 made about 100 horsepower at 4,000 revolutions per minute. if you were lucky and it didn't overheat first. Push it harder and you were playing Russian roulette with pistons and valves. Victor's thermally optimized engines? They were putting out 160 to 170 honest horsepower at 5,000 revolutions per minute, on the same displacement, same pump gas, same basic hardware. That's a 60 to 70% power jump from what was essentially a cooling system tweak. But power on paper is one thing. Real-world proof is another. Late summer 1946. That first customer, the guy who'd almost given up on his Lakes racer, took his Victor-modified Flathead to the Bonneville Salt Flats. Nothing fancy, stock bore and stroke, no blower, no alcohol fuel. Just the Russian hack in good tuning. He ran 138 miles per hour. In a Flathead. On pump gas. For context, the fastest Flatheads before this were scraping low 130s with every trick in the book, and usually blowing up shortly after. 138 miles per hour wasn't just fast. It was unthinkable. The racing community exploded. By fall, more modified Flatheads were showing up at Muroc, El Mirage, and Bonneville. They weren't just going faster, 10 to 15 miles per hour faster than identical cars running stock cooling. They were finishing runs. Stock engines would overheat, detonate, or blow gaskets halfway through a pass. Victor's engines just kept pulling, lap after lap, run after run. October 1946, Muroc Dry Lake. A simple roadster with Victor's mod set a new class record at 142.7 miles per hour. The previous record? 128 miles per hour. Same class, same rules. The only difference was coolant flow. But the most convincing proof came from endurance testing. One customer bolted his modified Flathead to a dyno and ran it at 4,500 revolutions per minute continuous for 73 hours straight. Oil temp stabilized at 220 degrees Fahrenheit. Coolant at 190 degrees Fahrenheit. Variation? Less than 2 degrees the entire time. A stock Flathead under the same load would have scattered itself across the shop floor in under an hour. Temperature probes told the story everyone wanted to hear. Stock exhaust port walls, around 550 degrees Fahrenheit. Stock intake port walls, around 300 degrees Fahrenheit. Victor's version. Exhaust ports, 625 degrees Fahrenheit, hotter, on purpose. Intake ports, 210 degrees Fahrenheit, much colder. The exhaust side ran hotter, the intake side ran colder, and somehow the entire engine was happier, stronger, and far more reliable. There was an unexpected bonus too, fuel economy. Because the intake charge was colder and denser, combustion was more complete. Modified engines used about 15% less fuel for the same power output. Racers didn't care much, they were chasing speed, not mileage, but it was further proof the hack was improving efficiency across the board. By early 1947, Victor had a backlog. He was only modifying 5 to 10 engines a month, not because he couldn't do more, but because he refused to rush. Every block got individual measurement, custom plug placement, hand-fitted brass inserts. He charged $75 per engine in 1947 dollars, over $1,000 in today's money, and people paid gladly. When your alternative was rebuilding engines every few races, it was the bargain of the decade. Hot rodders started calling it the Russian hack. Victor still called it thermal optimization. Either way, the secret was out. The Flathead wasn't obsolete. It had just been misunderstood, until one man in a Chicago machine shop decided to manage heat the way physics actually wanted. And when Detroit finally heard about it, well, their reaction was everything you'd expect from a proud giant suddenly realizing a nobody had just made them look very, very foolish. By early 1947, word of the Russian hack had reached Detroit. At first, the reaction inside Ford was exactly what you'd expect. Dismissal, bordering on laughter. Internal memos from the engineering department called it backyard tinkering and impossible gains from mere coolant restriction. After all, Ford had designed the Flathead. They had the best minds, the biggest budgets, the most advanced test facilities in the world. What could some immigrant machinist in a greasy Chicago shop possibly know that they didn't? They assumed the power claims were exaggerated hot rod hype. The reliability stories? Tall tales from the dry lakes. No way a simple cooling mod could add 60 to 70 horsepower and solve problems they'd accepted as unsolvable. But curiosity, or maybe worry, got the better of them. In April 1947, Ford quietly bought a complete Victor-modified Flathead through a middleman. No direct contact, no questions asked. They shipped it straight to Dearborn, tore it down in a locked lab, measured every brass plug, mapped every altered passage, and ran it on their state-of-the-art dynamometers. The results came back and matched everything the hot rodders had been claiming. More power, dramatically better heat management, near-zero valve seat recession, no cracking under sustained high RPM load, improved efficiency. Suddenly, the laughter stopped. Ford's first move was predictable. They tried to hire Victor. A well-dressed executive showed up at the South Side shop with an offer, good salary, benefits, a proper engineering title, the works. Work for Ford, help them improve the Flathead officially. Victor turned it down flat. He liked his independence. He liked working directly with racers and hot rodders. And deep down, after everything he'd seen in the Soviet system, he didn't trust big corporations, American or otherwise. Next, Ford's legal department got involved. Could they sue? Patent infringement? Trademark violation? Anything to stop or control this modification that was making their stock engines look obsolete? The answer came back quickly, no. You can't patent coolant flow. You can't sue someone for making your product perform better. There was nothing illegal, nothing even shady. Just clever machining. So they moved to Plan C, the classic Detroit playbook. Starting with the 1948 and 1949 developments, and especially clear in the all-new 1949 Ford overhead valve V8, and later the Lincoln Y-block, engineers began using thermal management ideas that looked suspiciously familiar. Separate cooling priorities for intake and exhaust zones. Deliberate temperature gradients instead of uniform cooling. Reduced coolant flow around certain exhaust areas. Thermal barriers to isolate heat paths. Ford never credited Victor. No mentions in patent applications. No acknowledgments in technical papers. The ideas were presented as original Ford innovations, the natural evolution of their own research. It was theft by silence. They weren't alone. General Motors engineers visited Victor's shop in late 1947, asking detailed questions, taking notes, measuring plugs. Chrysler sent an official delegation and even offered to license the process for their industrial and marine engines. Victor said no again. He wasn't interested in mass production or factory applications. He wanted his work in the hands of racers, hot rodders, people pushing limits, not buried in stationary generators or farm equipment. By 1948, automotive journals were publishing articles on selective cooling, optimized thermal gradients, and zone-specific heat management. The techniques were praised as cutting-edge advancements. Viktor Konstantinov's name? Never mentioned. Credit went to industry engineers and ongoing research at major manufacturers. But out in the real world, every serious flathead builder knew exactly where it came from. And as the modifications spread like wildfire through the aftermarket, something beautiful happened. It didn't stay a single man's secret. It became shared knowledge, passed from shop to shop, racer to racer, generation to generation. Detroit could ignore it, steal it, or rebrand it. But they could never stop it. Victor's hack didn't stay secret. It exploded through the hot rodding underground. He openly showed customers the process, exact passage locations, plug sizes, thermodynamics behind it. Racers took notes, made sketches, spread the word. By 1948, shops from California to Texas to Michigan offered Russian-style cooling mods. Most machinists learned second or third hand, yet the core idea stayed true. Variations appeared, copper plugs, partial blocks, tweaks for stroked cranks, some better, most close enough. By 1950, any serious flathead build included coolant redirection. It was no longer optional, it was standard. Magazines covered the technique but never named Victor, crediting the community. Victor didn't care about fame. He kept solving tough problems while his idea kept thousands of flatheads alive, competitive against new OHV engines. It became grassroots legend, knowledge shared freely, beating corporate control. The underground turned one man's insight into an era-defining revolution. Why this hack was pure brilliance? Victor's hack worked because it understood one truth Detroit ignored. An engine is a heat engine, not a power factory. Most fuel energy becomes heat. Victory lies in controlling it. Uniform cooling in Detroit's way was easy to manufacture but created huge temperature swings across the block. Exhaust side scorching, intake side cooler, metal fighting itself, leading to cracks, warping, valve failure. Victor embraced the natural divide. Hotter exhaust zone consistently, less thermal shock, longer life, better flow. Colder intake zone, denser air, massive power gain, no detonation. Blocked passages trapped air, perfect cheap insulation. No fancy parts. Just physics respected. His Soviet training helped. Optimize ruthlessly, no wasted resources. Outsider eyes saw what insiders missed. Simple, elegant, revolutionary. It didn't just fix the Flathead. It showed sometimes brilliance isn't complex, it's seeing clearly. The hidden Soviet connection. Here's the twist almost no one knew until years after Victor's death. His thermal hack wasn't entirely born in a Chicago shop. It was adapted from classified Soviet aircraft engine research he'd been exposed to in the 1930s. Back then, Soviet aviation engineers faced brutal challenges, high-altitude bombers operating in extreme cold, poor quality materials, constant shortages. They couldn't rely on exotic alloys like the Americans or Germans. So they mastered selective cooling and deliberate thermal gradients to keep engines alive under insane temperature swings. Victor had worked near those programs, designing related systems, reading technical papers. The math, the principles of zone-specific cooling, the use of air gaps as insulation, he carried it all in his head when he fled west. When he saw the Flathead's heat problems, the solution clicked instantly. Same physics, different engine. Cold War irony? While America feared Soviet technical superiority, a Soviet-trained immigrant was quietly using their ideas to make American hot rods faster and more reliable than Detroit ever managed. Victor kept it quiet. Talking about Soviet aerospace ties in 1940s America wasn't smart. But after he passed, old notes surfaced, calculations in Russian, references to Moscow Institute papers. Proof that the Russian hack was more Russian than anyone realized. One man transferred forbidden knowledge from Soviet skies to American dry lakes and changed hot rodding forever. Viktor Konstantinov died in 1978, age 70. His Chicago Tribune obituary called him a retired machinist. No mention of revolutionizing engine cooling. But his ideas never died. By the 1980s, selective cooling, zone-specific flow, and deliberate gradients were standard in high-performance engines worldwide. Modern cars use split cooling circuits, head and block cooled separately. Exhaust manifolds with thermal barriers. Prioritized intake cooling for density. Formula One, NASCAR, even economy cars, all trace roots to principles Victor pioneered with brass plugs. Computer simulation and CFD now do what he did with slide rule and thermocouples, but the core insight remains. Cool the parts that need it most, let others run at their natural temperature. Detroit learned, grudgingly. The OHV engines that replaced the Flathead incorporated similar thinking from the start. The aftermarket forced their hand. Victor never got credit in textbooks or patents, but every time an engine runs cooler, makes more power, or lasts longer because of smart heat management, his ghost is there. One quiet immigrant extended the Flathead's life, delayed the OHV takeover, and gifted the world a better way to build engines. Not bad for a man with just a lathe and fresh eyes. The story of Viktor Konstantinov isn't just about a clever Flathead fix. It's about institutional blindness. Ford had every resource imaginable and still missed the solution, because they were too invested in their own design to question it deeply. Victor succeeded because he asked a different question. Why does it fail, and can we fix it without replacing everything? Fresh perspective beat unlimited budgets. This pattern repeats throughout history. Outsiders, immigrants, aftermarket tinkerers, they innovate where corporations calcify. Detroit still ignores or steals ideas from the grassroots. They still believe bigger teams guarantee better results. But every once in a while, someone like Victor proves them wrong with simple, brilliant thinking. Innovation often comes from the edges, from people unconstrained by how it's always been done. Victor didn't need fame or fortune. He just wanted engines to work better. And because of that, every modern engine carries his unmarked legacy. The Russian who outsmarted Detroit didn't do it with money or power. He did it with clear thought, brass plugs, and the courage to challenge assumptions. That's the real hack. And it's one we could all use a little more of. Thanks for watching Torque Saga. Like, subscribe, and tell us your favorite underdog engine story below.